Okay, this is good.
Good morning.
Okay, so uh, I'll pass now. So Leah can start her last lecture. Right, only a bit of algebra. So please, Leah.
Thank you. I actually have to say that I will miss you. I really enjoy these talks and I hope that you did too. Even if you don't end up doing anything with graded classification conjecture, I hope that bits and pieces of the lectures are going to be useful to you. Okay, so let's finish this saga. Let's now finally talk about conjectures. So let's do one more example, one or two more examples. Let me remind you where we stopped yesterday. So we finally defined this graph monoid, which Rusbeck likes to think of as talented, which is isomorphic to isomorphism classes of graded function generated projectives, right? So there is this extra kick action of gamma there. And how is it defined? Vertices are generators, and defining relation is that every regular vertex is x times range of E. So here E is in source inverse of V as before. This is an R. My V's and my R's look similar. So this is pretty much the same relation as before, except that now we have that x, and that x is this action of our gamma, and our gamma for us will be infinite group generated with x, so it's isomorphic with z, right? And then we did one example last time towards the end of that session, right? We did one example. We computed this last time. Let me do just one other quick example, just because I really want to illustrate how this captures the lengths of paths. So let me take this graph here, and let this be U, V, and this is W, right? So this is also no exit. Actually, this one doesn't even have cycles. If there are no cycles, graph is said to be acyclic. So, there is one sink here, right? So we know how to compute the non-graded version of this, right? Let's see the graded version. So there will be two relations here because there are two regular vertices. V is not regular, it doesn't emit edges. And V emits only one edge to W. Emits only one edge to W means only one summoned. From V to W, length of that path is 1. That's how you can see the relation, tell you about the graph. But U emits two edges, right? So there are going to be two terms here. So one edge goes to V, and the other edge goes to W. So these are your relations, and if in a way, if you combine them, if you substitute what is V in here, right, then you will have that U is equal to x squared W plus xW. So actually that tells you that if you want to go from here to there, you can do it on two different ways because there are two terms, right? So two ways to get from U to W means two terms in here. And by here, I mean in this identity here. And moreover, these powers here, 2 and 1, tell you about the lengths of these two ways to get from U to W, right? So there are two ways to go from U to W. This is one, and this is another one. And this one has length 1, and this one has length 2. So you see these are exactly these powers here, 2 and 1. So you see that's the talent of this monoid. Let's do more examples before we go any further with conjecture. So my next 3 examples are going to match the 3 examples that we did with the good old K0, right? So if you remember, that was, I guess, Wednesday or maybe Tuesday class, doesn't matter. So before, we did K0 of Leavitt path algebra of this graph, and this graph. If you remember, these two ended up being equal to each other. K0s of these ended up being equal to each other, and this one ends up being trivial. So I want to do now the graded version of this, right? So now I want us to talk about K0 gamma of these 3 here. If you are looking at the pictures in my notes, this is the almond, this is the cat in the whatever, sleeping. This is the almond, and this is the rose. So let's do one at a time. So let's do first this very easy graph, right? So there is one vertex only. So talented monoid has one generator. Let's call it V. So if I have one generator, and if I'm thinking of it as some type of 1, what do I have here? I have 1, 2, 3, 4, and so on. But I also have x, 2x, 3x, and so on. And I also have x squared, right? Because I have this action by x, right? So I have all these things. And I also have negative powers. So kind of this goes in all directions, right? So what is this talented monoid in this case? Positive integer coefficients, non-negative in fact. It's monoid, so I have 0 also. And I have powers of x's, all sorts of powers, positive, negative. So your talented monoid is exactly this, right? There are no relations here, nothing else to add any other structure, right? So if I complete this to a group, then your group, remember that we shortened K0 gamma Leavitt path algebra of the graph, we shortened this to GE, right? So GE kind of comes when you just look at the graph and you pretty much don't need anything else, right? So GE, when you complete this integers, positive integers to a group, it's going to be all integers. So you see, this is your Grothendieck group with graded considered in this case. So you remember how it was before. Before, we didn't have none of these axes, right? Because there is no action or nothing. So pretty much your good old K0 was just integers, because your monoid was just non-negative integers, and then the whole thing was just integers. Now let's take a look at that cat sleeping. So let's take a look at example number 2, where we have not just that one vertex, but we have one edge. So pretty much we have a loop, because you see that poor edge has nowhere else to go but back to that one and only vertex that we have. Okay, so here we certainly have one generator. But now this generator is regular because it emits at least one and finitely many edges, in this case just one edge. So there is this relation, right? So your relation is telling you that V is equal to x, range of that edge one and only that v emits is again v, right? So this is saying that v is equal to x times v. So you see, in this case, this is telling you that that action by x is trivial. So that tells you that x doesn't do anything, right? So that pretty much gives you that x squared is also not going to give you anything, because if you are thinking what is x squared times v, well, that is just x times v, right? And x times v is v. And then x times v is again v, right? So x squared, x cubed, x to negative 55, they don't do anything, none of them, right? So pretty much your talented monoid here is only, if you're thinking of this v as 1, then your talented monoid here is only 1 plus 2 plus 3 plus whatever and 0, right? So it's just z plus. There is no action of x, so there are no x's there. And then your Grothendieck group is pretty much just integers. So you see how very different these two things are, right? This is our example 1, and this is our example 2, right? Very, very different structure we have. So you see that should illustrate how graded can help you distinguish between things, right? Because if you remember, non-graded was the same, and here it is very, very different. Let's do another example. Let's now take a look at that rows. So here we have still one generator. And now our relation is such that v emits two edges. So there is going to be two terms here. And one edge ends at v, and the other edge also ends at v. So if you remember, let me just remind you what happened before. So before we didn't have this x here, right? So this was just saying that v is equal to v plus v, right? So if we wanted to make it cancelative, then we ended up with in K0 level, we have that v is equal to 0. So pretty much that gives you that the entire K0 is 0. But you see here, that cancelativity is actually forced to hold already, because this side doesn't have x and this side has x. So you see, you will never, ever, ever in a million years end up in the situation that you have same things on the left-hand side and on the right-hand side. So actually, another talent of this monoid is that it's already cancelative. So something like this cannot happen in the graded case, right? So this is your relation, right? And then you're thinking how does a structure of something like that look like? What kind of structure what kind of identification we can have here? Just to try to understand what I will end up with a little bit better, right? So if I'm thinking that v is kind of like 1, then I'm thinking, right, so this is kind of 1, and I'm thinking this is 1 and this is 1. Then this action of x should be something like multiplication with whatever will give me 1. I mean, these two things added together should give me 1. So I can think of that action of x as multiplication with 1/2, right? So left multiplication by x is multiplication in this identification here is multiplication, or let's say not is, but corresponds to multiplication by 1/2. And I don't like this pale marker. Let me see if I have a better one. Okay, much better. So what kind of group you are going to end up with? What is your GE in here, right? It's going actually to be a set of all rational numbers that have only powers of 2 in the denominator, right? With this identification here, if we think of V as 1, and if we think of action of X by multiplication with 1/2, then we can have 1/2 present too. So you can think of this Grothendieck group as consisting of elements of this form, right? Where M is any integer and N is a positive integer. Right? And that actually this has a name like rationals or something, right? This is how it's denoted, right? So you can pretty much think of like what happens if you add 1/2 to a group of integers, right? What kind of ring you will get, and that's exactly the type of ring. So you see again, very, very different situation than before, because before looking at grading, we got trivial Grothendieck group, and here we have a very interesting Grothendieck group, right? If you want to try to play with this, if you want to try figuring out what happens with Grothendieck group, try looking at maybe this nice no-exit graph. Try to see what the relations are. Try to identify your group with something. And actually, you know what? If you understand this example well, then you will be able to compute pretty much Grothendieck group of anything no exit. So are we good so far? Just checking if there are questions. Okay, so now we can actually revisit that graded classification conjecture. Now we have seen enough examples. Let's revisit that graded. So it is saying that Leavitt path algebras of 2 graphs are graded isomorphic if and only if this K0 enforced with grading version of Leavitt of the Grothendieck group are isomorphic as pointed gamma groups. So this is the last thing pretty much that we need to talk about, right? And again, keep thinking, why would we care about this, right? Because determining whether two things like rings, algebras, or something like that are isomorphic or not, that's very, very difficult. So that's why people come up with all sorts of invariants, this one, that one, K0. And in this case, this K0 enforced with additional structure, because these are somehow easier to compute. See how we computed these things. We didn't even care about the Leavitt path algebra axioms and what is CK1 and CK2 and so on. We pretty much just played with graphs. We didn't even care that much about edges, right? The vertices here are kind of star of the show. So, so you see, that's why conjectures like this one, for example, are relevant. And let's the last thing that we need to talk about is what this pointed means, right? Because now we understand everything else, right? So this isomorphism here, let's maybe write that down. So this is as graded algebras, and this isomorphism here is as pointed gamma groups. So we talked about so group, there is plus there, right? It's actually a billion. gamma action we understand now, right? So this is the last thing on the agenda to say what that is. So, the pointed part comes from the a pre-order that ordinary K0 and this fancier version of K0 both have. So this comes from a pre-order. What is pre-order in general? What is pre-order in general? That means that you have a binary relation. In this case, we will say less or equal to, which is reflexive and transitive, but not necessarily anti-symmetric, right? So order without pre is reflexive, anti-symmetric, and transitive, and pre-order is just reflexive and transitive. And there is a very, very, very natural pre-order here. So you're thinking that one finitely generated projective is less or equal to another finitely generated projective if and only if P is a direct summand of Q. So that's your pre-order. And there is a very special element of this K0, and for that matter of the non-graded version of K0. I have to erase something, so something has to go. So you see, this definition here doesn't really matter that much if your K0 is graded or not, right? Let's just say that if it is a graded version, then it would be these two would be graded, right? And P being isomorphic here, remember when I say is, I really mean is isomorphic to a direct summand because these are isomorphism classes, right? Let's maybe write that down. So if it is non-graded version, I'm just thinking isomorphic to, and if it is graded version, then I'm thinking graded isomorphic to, right? And then you're fine in both worlds. So there is a very special element. Let's just talk for a moment of K0, right? There is a very special element here, which is kind of your generator of everything finitely generated free, right? So this has a special role. Because pretty much every finitely generated projective is direct summand of some finitely generated free, right? That's pretty much how we defined projective modules, right? So if it is finitely generated, then you can find that free to be also finitely generated also. So pretty much this means that for every P, there is n positive, positive actually integer, well, non-negative, let's say. So there is non-negative integer here. Why did I say non-negative? Because that P can be 0 to start with, right? That's what gives you non-negative, not just positive. So for every P, there is n such that this holds, right? And what does that mean when you go to level of K0, right? For every element, let's call it A, there is n, such that pretty much you can squeeze that A in between minus n and n times this r, right? So this r on n, this is like r plus r n times, so we can write it like this. So an element of a monoid that has this exact property, right, that this element here has, is called an order unit. And if you are in a group, this is an order unit. If you can pretty much squeeze every element in this type of interval determined by order unit. So when you say pointed, and I'm going to go to graded case in a second. So when you say pointed, that just means that your K0 is considered with some special order unit. And because this is always going to be, I mean, there can be other order units, not just this special element, but we are always going to consider this R here, right? So with order unit just means that you are not looking at the group alone, you are looking at that group with some order unit. Now let's see how this relation is going to look like in graded case, right? So let's talk about K0 gamma now, where this still has a special role. We'll just see in which sense. So everything is pretty much the same. The story goes exactly the same way. The only difference, let me highlight that in another color. The only difference is that this will look different. So remember how finely generated free look like if they're considered as graded modules. Then copies of this R have those shifts, right? So the only thing that I have to change in my definition here is how this side looks like, right? So there is n, and there are gamma 1, gamma n in your gamma, such that P is direct summand of R gamma 1 plus R gamma 2 plus R gamma n. That's the only difference, right? Now, how is this element going to look like when I think of the structure in my monoid? How do I add? How do I shift, right? What is this equal to, right? So direct sum becomes sum. This element R gamma I becomes pretty much gamma I times R. So this is what I'm going to have here exactly, right? Gamma I times this R. And since some of these gamma i's can be equal to each other, if I want to combine them in you know, if I want to bundle them together and consider them as one term, that's fine. So if I'm thinking of how this looks like a positive integer times some elements of the group that are then, let me call them j, just so that we don't think that that's the same I. Times elements from the group, right? So this, if you're thinking how this element is going to look like for us, remember our gammas are just x on n's, right? So if gamma is equal to x, which is isomorphic with z, then these here are going to be just some powers of x, right? And for different j's, let's call them, I don't know, mj's, different powers of x. So these are like Laurent polynomials with positive coefficients, so pretty much they live here. So how are you going to define order unit in the graded case? You're going to say, well, for every p there is n, and there are these like powers mj here, such that p is direct summand, p is less than equal to of this type of element times r. So that's what order unit is. And what does it mean pointed in the graded case? Same thing, except that you are going to put that gamma there. So the order unit itself is still the same thing, same special element here. So just before I tell you about the state of conjecture and what's known, what's not known, let me just do one example so that we see why this pointed business matter. Why without pointed, we would know that that conjecture would be false. Why pointed matters. So let's take a look at two graphs that we have considered now many times before. This one and that one. So I think that we computed monoid for this one before. Let me just remind you. So if this is u, v, and w, then you have that u is equal to xv, and v is equal to xw. So I can eliminate v from here, right? And I can say, aha, that's going to be x squared w. So I pretty much have only one generator w. So I can consider only w as generator and no relations. So that means that your monoid is going to be, there is no relation, so you have all of those axes there, right? This is the monoid. And the Grothendieck group is going to be the same thing, but without restricting the integers to only non-negative, but all of them. Now, if you do the same exact thing in here, let's call this W and this U and V. So here your relations would be, there is one edge from U to W, right? And there is one edge from V to W. So again, you can eliminate U and V because you can express them in terms of W. So the only generator is W, and there are no relations, right? So your G is going to be the same exact thing. So you see here, you can say, well, it's not much of a conjecture because if you know, even in this like relatively simple case, we are getting the same graded Grothendieck group. Even with grading, they are the same. But now let's consider, let me just erase the relation now. Okay, so it's the same, right? Let me just leave it in here. So you see, now let's think about what is that order unit, right? So order unit is always R. And if we are thinking in terms of idempotence, right, then this is like 1 times R, right? That idempotent times R, that's 1. And now if we remember what is identity in for Leavitt path algebra, so I think that maybe at this point I'm kind of ideally, we would need some time to digest this material because now I'm going to say, oh, we did that on Tuesday. And you heard so many things in this on other courses since Tuesday that you are probably like, oh, Tuesday, when was that? 3 million years ago? So let me just remind you that in Leavitt path algebra, the identity is sum of vertices. So, so that 1 is your U plus V plus W, right? And if I now think of the relations that I just erased, so from U there is path of length 2 to W. From V there is path of length 1 to W, and W is just W, right? So, so here I have polynomial x squared plus x plus 1 times W, right? So somehow, if I'm thinking of that W as some type of 1, then this group here, if I consider it with order unit, with like 1, this type of 1, then it's going to be this, right? X inverse. And that 1, this one here, let's put brackets around here so that we are thinking this. And that is equal to x squared plus x plus 1. So you see, this polynomial kind of has some special significance for this graph here. Now let's see what polynomial has special significance here, right? So here your order unit, that 1 is equal to u plus v plus w. And here u is xw and v is xw also, right? So this polynomial here is 2x plus 1. Very different polynomial here, right? So if you think what is your pointed Grothendieck group here, it is not only z x inverse, because that part doesn't distinguish between the two, but these polynomials that are order units, in this case, that's what makes a difference in this case. So you see, that's why pointed really matters. And hopefully, you know, since we have seen how to compute this order unit in these two examples, I think that if you ever in your life want to do this on your own, you can just go back to notes and and have hopefully an idea how to do it. Here, I want you to try, if you are interested in playing with this, try to compute order unit for these two graphs. This one that I recommended you to do just to compute the Grothendieck group, and this one here. So if you compute the Grothendieck group, you will see again how these two are different. If you remember, a regular case 0 doesn't distinguish between these. Okay, and now for the last 20 minutes or so, let me just tell you the state of this conjecture, what is known, what is not known. Let me relate it to you with another conjecture called Isomorphism Conjecture, and pretty much then we can close this series.
Yeah, just before that, I have a question. When you compute this pointed K0, whenever you have different polynomials, then it's not going to be isomorphic as pointed.
That's pretty much, yes. But that also requires some arguments, right? Because if you remember when we were computing matrices and they have these shifts, I made a point like, okay, well, these are different. Does that automatically means that they are not isomorphic, or that doesn't automatically mean that? So same kind of question is relevant here too. But if this is the same and this is different, you can safely assume that they are not isomorphic as pointed Grothendieck groups. But very, very good thinking.
Thank you.
So this conjecture has been formulated in around 2011, I believe, in a paper by Rusbek Hazrat, your speaker next week. If you want exact paper, I have reference in my notes. So Graded Classification Conjecture formulated 2011, I believe. And he showed that it holds for a class of finite graphs that look like no exits, except that you can put on your sinks, you can put roses. So he called them polycephaly graphs. This polycephaly means multi-cephaly heads, so like multi-headed. So how do they look like? So you have paths, right? leading either to a sink, either to a cycle without exits. You can have, if this has more than one vertex, you can have entrance from in another way to another vertex. That's fine. As long as I don't have exits, that's fine. So something like this, let's say, would be no exit, right? No exit. Every path leads either to a sink or a cycle without exit. But if I have polycephaly, then I can put the rows. Let's do like maybe 3 petals. I put the rows on top of a sink. So now every path leads either to a rose, to a cycle without exits, or to a sink. And I think that Rusbeck saw kind of like heads. So these 3 would be 3 heads here. So he's thinking multi-heads, so that's why polycephaly. Because of these multi-heads, I always think of some type of dragon with many heads, and these graphs always look scary to me, but that's the name, that's how they are called. And now actually you can have a maybe even an idea of why would this be true for these type of graphs. So you see these things, they correspond to matrices over K only. And remember, now we can have these gammas in the back, right? No exits, they correspond to matrices over X on N, where N is how long your cycle is, and then we can have these shifts in the back. And roses, they correspond to matrices over Leavitt algebras, which are kind of Leavitt path algebras of only roses. These Leavitt algebras are denoted Ln1. So N is the number of loops in here. And then you can again have the shifts. And because when you sit down and compute K0 gamma of all of these things, then the graded classification conjecture works. That's why it's going to work for finite sum of all of these too. So pretty much that's, I mean, proof is way, way more involved, but at least it gives us some idea. You see, somehow we represent them by matrices and then it works. And then a few years after that, Ara and Pardo, Pere Ara and Enrique Pardo, they showed a weaker version of the conjecture for finite graphs without sources and sinks. So you see, if this doesn't happen to have a source, and if there are no sinks, then you see those polycephalies would be in this class considered by Ara and Pardo. But it is a weaker version of conjecture. And if you are thinking weaker version in which sense, again, I have a reference for you, take a look, and then you will find out. So the class of graphs is different, right? So there are polycephaly that do have sinks and sources, and there are graphs without sinks and sources that are not polycephaly. So you see, that's why both of these 2 results are relevant for the conjecture. And then again, a few years passed by. At the time, I didn't know anything about graded rings. So then somehow Rusbeck and I started talking. So he was well versed with graded rings, and I was always interested in the stars, in evolution. So somehow we ended up talking about, well, these Leavitt path algebras, in a way, they have both the grading and the star. So what would happen if we consider both of these 2 structures together? And then we actually start thinking about the graded classification conjecture star version of it, which would actually ask Leavitt path algebras are isomorphic, not just as graded rings, but graded star rings. So let me say as graded star rings, if and only if the K0 gammas are isomorphic, right? But again, now you have to consider some type of structure that is present in your case 0 based on star. And in vast majority of cases, that action of star is kind of trivial. So that's why you don't have to do anything special about star in terms of conjecture. But this is certainly stronger because this direction, by the way, always holds. So if you want to go back, you want to go back to more. So that's why this would be stronger than the graded classification without star. And so, and then Rudbeck and I showed that graded classification conjecture star, so without star as well, holds for no exit graphs, row finite, no exit. So what do we have here? We have paths. Every path leads either to a sink or to maybe cycle without exits. But this time around, it is not finite. So you allow this other version of sinks called infinite sinks, which is some kind of path, keep going forever, but it doesn't lead you anywhere outside this one direction here. So it has no bifurcation after a while, right? Maybe it has bifurcation here, but not after a while, right? In the long run, it doesn't have bifurcations. So, and it is row finite. That means that you can have infinitely many paths coming in. So you can have something like this, right? I mean, so, right, so you can have infinitely many vertices as well. So row finite, no exit, such that every infinite path ends in a cycle or a sink. But sink now in this sense, finite or infinite sink. So this would be a real sink, finite sink. And this would be infinite sink. So again, this class is different than polycephaly because this one doesn't have roses, right? But on the other hand, this allows you to look at infinite graphs as well. So that's like, all these results, one is bigger in some sense, smaller in some other sense, so they're all different. And the last result that I will mention to you, the last step towards the graded classification conjecture, is in the work of Soren Eilers, Efren Ruiz, and Aidan Sims. Very recent result. I think it is. It appeared on Archive in 2020. So let's write that down. You have complete reference in the notes. So they show the conjecture as well as its graph sister algebra version, right? Remember graph sister algebras? Most of the things that I'm telling you in this talk, they hold for graph sister algebras as well. So they show that the conjecture and the sister algebra version holds for some type of graphs they called amplified. So these amplified graphs, they are countable in the sense that you allow only countably many vertices and edges. And again, these amplified graphs, they are again different class than all these other classes that I mentioned. So if you want exact definition, you will have to go to their paper, take a look. You have reference. But let me just leave it at that it is all different, right? These classes are all different. So what is very promising in my eyes is that, you see, there was this one class, and there is another class, and there is another class, and each class makes the class of graphs for which the conjecture holds a little bit bigger, right? So you see, it seems that it keeps growing. So if we are to go to all graphs, we are not there yet, but it is promising. So for the end, let me relate it to another conjecture called isomorphism conjecture. Because if you manage to prove graded classification, then this isomorphism conjecture will hold. So let's relate graded classification conjecture with isomorphism. So isomorphism conjecture has been introduced by Mark Tomford and Gene Abrams. Their photos you have on page 20 if you want to see how they look like. Now they're together at University of Colorado in Colorado Springs. So Tomford and Abrams. And I think that this conjecture is approaching maybe its 15th anniversary or so. That's how old it is now. It has been conceived pretty early on, because after Leavitt path algebras were introduced, because people were always curious in this connection between Leavitt path algebra and its graph C-star algebra. And if we are interested in conjecture, in the connection, then we better put complex numbers here, because you see this is kind of always over complex numbers. So you are curious about this. So they actually asked whether two Leavitt path algebras, let's put them over complex numbers, are isomorphic as rings if and only if their graph C-star algebras are isomorphic as C-star algebras, so as star algebras in this case. So you see, very kind of relevant question if you are thinking in terms of finding the connection between Leavitt path in pure algebra world and C-star, graph C-star in the world where you have norms and some type of topology and all of that. So what always holds, is that if two Leavitt path algebras over complex numbers are isomorphic as star algebras, then you can get that C-star algebras are isomorphic graph C-star algebras. So you see, because of this always holding, then if you want to formulate isomorphism conjecture without even talking about C-star algebras, you can just ask, so if I can always go from Leavitt path algebras as star algebras to C-star algebras as star algebras, then it's enough for me to think about whether this bridge can be crossed from as rings to as star algebras. Right? If I'm not super familiar with C-star algebra world, I can pretty much formulate this isomorphism conjecture without even mentioning the graph C-star algebra. So that would be then conjecture for you, right? So we are in purely Leavitt path algebra world. And then if you want kind of the generalized version of it, then you don't even have to put complex numbers. Because if you remove C-star algebra from the picture, then it doesn't matter what field you are in, right? So we can then erase C, and we can just put any K, right? So are these isomorphic as rings? Exactly, if and only if they are isomorphic as star algebras. But then, people said, well, you know what? If I'm interested in getting from rings to star algebras, let's first make sure that we can get to algebras alone. So then they actually start talking about this without even a star. So this statement that now you have in front of you is known as like generalized isomorphism conjecture. Two Leavitt path algebras isomorphic as rings if and only if they are isomorphic as algebras, right? And finally, if you are into grading, then you can have the graded isomorphism conjecture. When you just add graded here and graded there. And that would be the one that would follow from graded from classification conjecture. So this conjecture here, right? This conjecture here, let's call it graded isomorphism conjecture, right? So this conjecture here follows from graded classification conjecture. And because the proof of that is literally one line long, I want to show you the proof. So why graded classification conjecture implies graded isomorphism conjecture. So let's assume that graded classification conjecture holds. Let's try to prove this one here. For this one here, one direction always holds. So if they are isomorphic as algebras, then of course they are isomorphic as rings. So this always holds. So pretty much if I'm to show that graded isomorphism conjecture hold, I need to show this direction only. So let's assume that that Leavitt path algebra is isomorphic as another Leavitt path algebra as rings, as graded rings. So if they are isomorphic as graded rings, then their pointed case 0 is the same, because same rings should give you the same case 0, and that holds for graded case as well, right? So if two graded rings are isomorphic, then you have that their case 0, gamma, pointed, not pointed, they are isomorphic. But what is graded classification saying? Graded classification is saying if K0 is isomorphic, then I have that they are isomorphic as graded algebra. So this now directly from graded classification conjecture, which we assumed it's true, is telling you that then Leavitt path algebra 1 is isomorphic to Leavitt path algebra the other as graded algebras, and that's the end of the proof. So that's how, if you manage to show this one, then you know the other one. That would be really, really cool. So I planned, you will see in the notes that I planned for you something about irreducible representations of Leavitt path algebras as well, but it would be definitely, now I see too much to bombard you with information on that too. I do want to just quickly point your attention to the definition of a branching system, which is something you can talk to your organizer Daniel with, because he's really good at that, trust me. And I think that it is a great way to learn, to start developing a sense of modules over Leavitt path algebras. So in this little course, we talked only about like algebras. We didn't talk about modules that much. But if you're trying to see one very nice way to generalize tons of modules over Leavitt path algebra, then you can use these branching systems. That's very natural, very nice. And actually, branching systems are enough for you if you're interested in simple modules, as well as if you are interested in graded simple modules. Or if your cup of tea is more representations than modules, then whenever I say module, you can say representation, and whenever I say simple module, you can think irreducible representations, so you have them all. But it wasn't in the books for us to cover that too. So then let me stop here. Let's see if we have some questions maybe about these conjectures or anything else.
All right, so anyone has any question, comments? Oh, there we go.
Hello. Hi, Leah.
Hi.
This is Alfiljan. So thank you for your talk. We enjoyed so much the entire week. Me and my colleagues here are talking how much we enjoyed how you explain everything. So thank you so much for that.
Oh, you're very welcome. It was
Okay.
a pleasure.
So like I think it was Tuesday that Danny Van Wyk man we learned in his talk about Steinberg algebras and the groupoid associated to the graph. So we learned in that lecture that the Leavitt path algebra is isomorphic to the Steinberg algebra of the groupoid, essentially. So it got me thinking, because of all of this classification conjectures, are there already like some attempts on the classification conjecture via the Steinberg algebras?
I'm sure that there are. I'm sure that there are, absolutely. And I'm sure that people are trying to say, well, if these questions are relevant for Leavitt path algebra and this Steinberg thing is more kind of general, then, well, so let's see. Is it the groupoid if and only for Steinberg algebra, if and only if some type of invariant like K0 or the K0 itself? I'm sure, right? In my personal feeling about this is that we still don't know this one. So maybe we should first cross this bridge. But on the other hand, you never know. If maybe somebody crosses this bigger bridge over a larger river, then this is just going to trivially follow. So pretty much that's how much I know about that.
Okay, thank you. I have also another question, because
Sure.
when you wrote the word no exit graph, and if I correctly remember it, is that every vertex leads to the cycle and stuff, and my eyes sparkled, because in Lie brackets, if you remember the stuff I sent you, is that
Uh-huh.
there's already results regarding simplicity via Lie brackets. So, and we learned today that it is already, the conjecture is true for those graphs. So I was wondering if also in the point of view of Lie brackets, that maybe there are some attempts on the conjectures as well.
I'm sure that a lot of people are thinking about that, because you see, somehow more and more people are getting interested in this. And I will give you like my perception of what's currently happening. So somehow, even if it's not necessarily polycephaly, somehow everything depends on cycles that have exits that return, which are called extreme, which are kind of like roses, cycles that have exits, possibly, but they don't return. And that's why, if you are interested in this, that's why I recommend going over that last part of the notes also, because these are called exclusive cycles. and like the sinks and sinks and acyclic part. So these are, in a way, two opposite sides of spectrum if we come to cycles, right? In general, cycle, if it's not no exit, then it can have maybe some exits that return and some exits that don't return. So in general, it's a mixture of these two cases. But my feeling is somehow that if we understand the two extremes, then we will be fine with everything else. And I do think, and I think that you know that well, that talented monoid can help with that very much, because these type of cycles, monoid recognize them. And monoid would even recognize if something is in between. So that's why I think that, you know, that's why I think Rusbech and Huan Li, his collaborator in another talented paper, they were trying to describe the cycles via monoid. So so I think that thinking about what happens with cycles and with these things, I think that may be a way to go.
Okay, thank you, Leah.
Sure.
Okay, any other comment?
I also have a question.
Sure.
Can you have two different graphs that they are the Leavitt path algebra are isomorphic with respect to one field, but not isomorphic with respect to a different field?
With respect to different, I didn't hear that last word that you said.
Yeah, if you change the field K, can the algebras be isomorphic with respect to K?
Okay, that's actually also subject to yet another conjecture. So it's called like field dependence conjecture. So the question is if Leavitt path algebra of E is isomorphic with Leavitt path algebra of F over K, and K1 is another field. Is Leavitt path algebra of that other field isomorphic with Leavitt path algebra of that other field or not? So this is called field dependence conjecture. So one way how people were trying to cross this bridge is saying that every field is kind of like K crossed with Z over Z, right? So that's how you can kind of reduce your question to commutative rings, and in particular to this one commutative ring that is kind of special, right? So so that's one way to think about this. And in all sorts of attempts, the answer always came up as, well, yeah, they kind of do look isomorphic. One aspect of fields that can distinguish between algebras is if you look at these fields together with involution. So you see, Leavitt path algebra has involution, but if you change involution of that field, you are changing the involution in algebra as well. Let's just see what is that involution in Leavitt path algebra. So every element of Leavitt path algebra looks like this, right? So if I'm to star this whole thing, I should be able to star element from K. So this is where involution on K depends, and PQ star star is Q star star, which is Q, and P star. So you see, this is kind of default, and this is where differences may happen. So if you, I think that I have that in one or the other paper written down in details, but definitely what I can hopefully convince you of in here is that if you take complex numbers with identity and complex numbers with very different involution, which would be complex conjugate involution, then it's kind of, you know, straightforward that these two algebras will have different structure, right? So far, the only aspect of a field that really impacts the whole Leavitt path algebra is presence of involution. And the only ring theoretic properties, if you remember, I think it was during that Wednesday afternoon chat, not during lecture, so I'm not sure if you heard that part. So one aspect of research in Leavitt path algebra is if you have some ring theoretic property such that Leavitt path algebras has it, you want to find graph theoretic property such that graph has it, right? And you see there is k here and there is no k there, right? So you can also say, well, what happens with k here? So don't we want to say, and k is such and such? So the only properties that really need this other part here are properties that have a star in them. So if you say is Leavitt path algebra star regular or star bare starring, doesn't even matter what these things exactly are. But I just want to emphasize that there is star in all of them. Then k matters, right? Then it is star regular if and only if a is whatever, a cyclic, and that involution on k somehow is more like this one than like that one. So that's the presence of field, that the properties where presence of field really matter.
Okay, so thank you.
Sure.
Okay, so any other question? So Leah, thank you very much. We're gonna last thing for you again.
You're very welcome. If anybody thinks of a question, just email me, and absolutely that would be great.
Okay, will do. Perfect. Thank you for the set of lectures. It was great.
You're very welcome.
Right.
So have a good next week. Have a good weekend now, and then have a good next week. Bye.